Okay, so this is our second lecture of the day, and it's Michael Atiyah on Chern classes of real vector bundles. Michael.
Well, when Andrew asked me to take part in this double act following Rob Kirby, I agreed, and then I decided to talk about what I was working on, but of course I didn't finish what I was working on by the time of the talk, so but anyway, what I work on will be too technical, so this is going to be a rather elementary description. I'll keep away from difficult things, try to put it in general context. Now, Rob Kirby's talk, you heard a lot about the mod 2 invariants from, which had different names, but they all went back to half, in some sense. And this is about, to be also about mod 2 invariants, which are not unrelated, but start with kind of a different origin. So let me start with this situation here. The title, by the way, is the Chern classes of real vector bundles, and the important thing is the real has a capital R, big R. So Andrew was trying to growl out with a capital R, but he didn't do a very good job. Now let me start off with the first fundamental theorem of algebra, as they're called, which says that a polynomial with a complex in variable z of degree n has always n roots. Now, of course, there's a typical polynomial of degree n written out, which not all the coefficients would be 0, of course. This is only true, of course, so long as we do three things. First of all, we must use complex numbers. Otherwise, we wouldn't always have n roots. Secondly, we must allow infinity sometimes. For example, if a0 is 0, then one root goes off to infinity and we lose it, unless you can include infinity. And thirdly, we must count multiplicities. If two roots coincide, we have to count multiplicity 2. With those three assumptions, every polynomial has n roots, and that's the basic theorem of algebra, and then algebraic geometry. Everything starts from there. Now, if you work with real numbers, of course, real coefficients, ai, and look for roots z which are real, then of course the number of roots is not always n. All you can say is the number of roots is congruent to n modulo 2. So if you have a quadratic equation, it may have 2 real roots, or it may have no real roots, or a coincident root which counts twice. If you have a cubic equation, you will have at least 1 real root, and you may have 3. So this is a fundamental difference. The real numbers are much more difficult from this point of view. Of course, the origin of that statement is easy to understand geometrically. Why do the complex numbers appear from the point of view of geometry? If you take a polynomial equation, then you think of the solving that equation as you draw the graph of the function, the left-hand side, and that gives you a certain curve in a plane, and then you look at the line constant 0, and where those two lines cross is the solution to the equation. So two lines crossing and counting multiplicities of intersections is the same as counting roots. Now, if you take two lines, when they come to cross, you don't know what to assign, a value plus 1 or minus 1, without some choice of orientation. And that isn't available in general of the real numbers, so you can only work modulo 2 because you don't know the difference between left and right orientations. Over the complex numbers, it's the great beauty of complex numbers from the point of view of topologists, is that the complex plane comes with a natural orientation. You multiply by I, that rotates the plane through 90 degrees in one direction. By the convention, we rotate clockwise. So that's the complex numbers have a natural orientation. That's why complex roots can be counted as integers, not just modulo 2. That's the sort of geometric, and that's very important for all the geometrical ways of thinking about it. So we have this fundamental fact that over the real numbers, life is much harder than over the complex numbers. And so what mathematicians have done for 200 years is they've taken the easy route. They say, well, we can't solve the problem we originally want to solve about how to find real solutions. We'll do the easier one, we'll find complex solutions. So you may say that the mathematicians cheated and avoided the issue. But anyway, complex algebraic geometry, which means you study, of course, more variables and more equations, is now a very elaborate, rich theory which has been developed for 200 years, and it goes back to the work of Abel, Riemann, Lefschetz, Hodge, Serre, Gründing, up to the modern time. This is a big very powerful, successful theory. And it's gone in tandem with topology. Now, you see, people who are young chaps like you don't have a kind of perspective of the old guys like me. You know, you didn't talk to Gauss and all that. So if you look back at the history of algebraic geometry, the two things went together. Algebraic geometry was there, people wanted to solve problems about algebraic geometry and number solutions. They developed the tools which became tools of topology. And most theorems in topology had their origins in algebraic geometry, and the two went hand in glove all the way through. Intersection theory, homology, all of it. Lefschetz, for example, is a name well known to topologists, but he got into it because he was interested in algebraic geometry, complex variable theory, and so on. And Abel and Riemann, of course, had developed topology at the same time as they developed the theory of complex algebraic functions. So it's very important that topology really went alongside with algebraic geometry, and of course nowadays we have physicists thrown in as well. Their algebraic geometry is turning up in physics, so it's broadened its scope. But real algebraic geometry, over the real numbers, is a poor relation. Not very much has been done. But I remind you that amongst Hilbert's famous list of problems in 1900, his 16th problem was in fact about real algebraic curves. You take the projective plane, by the way, incorporates infinity, so that stops that. And then you take curves in the plane, degree n, you can draw the curve, it's now real, it's genuinely something you can draw, and it'll break up into a number of components, and if you have the number curve of degree n, then the number of components it has maximum possible value, one more than the genus, which is given by that formula up there, and so you can draw pictures. Of course, some of them may not be there, if it's missing some components, but you can ask, given the number of components, for example, when it's the maximum, how do they interrelate? And you see two examples there showing you can have three ovals which you just separate, or you can have three which nest in one inside the other. Now, obviously, lots of different combinatorial possibilities. And Hilbert's 16th problem was to find out, for a given integer, even n, let's say, what the possibilities were. Originally, the first unknown case really was the curves of degree 6, when there are 11 components maximum, and how many possible configurations are. One time they felt there were 2, then they discovered there were 3, and this has been still an unsolved problem. People worked on it. So it shows you how little progress has been made with real algebraic geometry. It's still struggling with curves in the plane. Now there has been some progress in the past few decades, and it's mainly by the Russian school. And they see here some names which are familiar. The Russian school, with people like Petrovsky, who did a lot of work on differential equations, and in fact differential equations lead you to algebraic geometry through characteristics. But then Rocklin's name, which you just heard, in connection with the Rocklin's invariant, and then more recently there is Gudkov, who worked a lot on these kind of questions, and Arnold, who's contributed to it, and quite a big school, mainly Russians and rather little done outside Russia. Some cultural reasons. And the key thing for progress there, after the early days, was that people tried to use the information about the complex curve, the complex Riemann surface, to get information about the real part. So you climbed on the shoulders of the work done in complex analysis, because the one thing you do know about a real curve is the real part of a complex curve. And so you try to see what you can exploit. And that's where some of the progress has come from, and some little steps forward until the 16th problem. But the general program is still vastly unknown territory. So this is a general program, if you like. I'm doing propaganda for it, I'm not going to give you any answers really. To use modern methods of complex algebraic geometry to derive results about real algebraic geometry. That is a program, but it's a hard program to define because over the real numbers you don't expect to prove the same things. You can't prove the number of solutions is equal to this. You can prove it's not more than that. You can get inequalities, and you can ask about these, like the 16th problem of Hilbert, relative positions configurations. So it's not quite clear what the questions are, but you have this large amount of beautiful theory for the complex case developed, and that's where you can start. that's the kind of background framework of what I want to talk about. Now, the best place to start, and don't forget the title of my talk had the word real, I'll explain what that's related to talk about real solutions, but it also had the word vector bundles. Now, the best place to start is to talk about line bundles. See, because if you look at algebraic geometry, as we discussed originally, corresponding to curves, and if you agree that you work over the complex numbers, you have to use complex coordinates, and if you agree you want to work including infinity, you have to work in the complex predictive space, and so you could take n equal to 2, then it would be the complex predictive plane, and you have 3 homogeneous coordinates to specify point in the plane. Only the ratio counts. That's how you, you have 2 points, z0, z1, defining the complex line, then only the ratio counts, and if you have 1 and 0, that gives you 0, you have 0 and 1, that gives you infinity. Infinity is built in. But there is, of course, the ambiguity that the multiplied by a constant doesn't alter the point. And then, of course, you consider equations, which are now homogeneous equations, because that's the only one that makes sense if you multiply by a fixed constant. And so, a curve in the plane is given by a polynomial, the homogeneous degree, whatever it is, k, let's say. Now, the point is that the homogeneous coordinates familiar to algebraic geometers are not functions. Because if given a point, the value of the homogeneous coordinate is unspecified up to a multiple. What it is, from the modern point of view, is a section of a line bundle. And over the vector space, there is a natural canonical line bundle whose sections are these coordinates, the linear forms of the coordinates. More or less by definition, because complex vector space is defined as a quotient of vector space, or when you take all the lines through the origin in a vector space, they give you complex vector space. The lines themselves form a line bundle, family of lines. Actually, what we need here is not that line bundle, but it's dual. Anyway, it's the line bundle whose sections, in fact, holomorphic sections, are precisely the coordinates. And then if you want to take a line bundle polynomial higher degree, that can be viewed as a section of the line bundle you get by taking the original line bundle, called H, and tensing with itself k times. That's still a line bundle, it's a family of lines, and the section of h to the k is a homogeneous polynomial of degree k. So the notion of homogeneous polynomials leads us naturally into the notion of sections of line bundles, and these you can do in any context you like. I will move rather easily between talking about analytic things, holomorphic things, algebraic things, sometimes purely continuous, topological things, but the notion of a vector bundle or line bundle is more or less the same in any category. You have a parameter space. Over that parameter space, you have a family of vector spaces, varying with the point. The dimension remains constant. Locally, it looks like a product, but it's twisted globally. And vector bundles form the natural framework in which to study originally classical predictive geometry. And so this is the way you define a hypersurface of degree k as a section of a line bundle on predictive space. Now, in general, if you have a line bundle L and you take a see my number is right. The section will vanish along some hypersurface, which we called Y here, and the homology class of this hypersurface, the surface of complex dimension 1 less than the whole space. So if you're in predictive n space, it will have dimension 2n minus 2 real dimensions, and it defines a cycle, homology class, in the complex vector space, and the complex vector space has one generator and homology in every dimension, so you can think of that as an integer, and that's called a degree, and if it came from a polynomial of degree k, it will correspond to the integer k. So all this is that's a relabeling of the word notion of degree, but it's one which works at much greater generality. So the surface is dimension 2n minus 2, that homology class. Nowadays one prefers to take the dual, the co-homology class, whose dimension is then complementary, And so a line bundle gives you rise to a class of dimension 2. This line bundle is what's called the first Chern class. And you can do that, as the green indicates over there, any complex manifold, any complex dimension n, any holomorphic line bundle L, any holomorphic section S, L, with a zero set Y, the class of Y in the cohomorph H2 is called the first Chern class. And the point is, it's quite easy to see, that it's the Chern class is the only topological invariant of the line bundle. Two line bundles are topologically equivalent if and only if they're the same Chern class. So Chern classes are another way of encoding the information about the twisting taking place in a line bundle. And here I'm talking about holomorphic things, pointing out at the bottom that in algebraic geometry you're dealing with algebraic things, but Serre proved a very general theorem, which is a sort of ultimate generalization of Liouville's theorem, which says that a holomorphic function on the sphere is constant, and in general, holomorphic and algebraic mean the same thing. If you're dealing with complex vector spaces, complex vector varieties, then anything which is algebraic, automatically holomorphic. Everything that's holomorphic and defined everywhere is automatically algebraic. So you don't need to distinguish between one and the other. The holomorphic theory is one you do with over the complex numbers. The algebraic theory is one you can do over arbitrary fields if you're inclined that way. So I'll slur the distinction between algebraic and holomorphic, but a lot of the time I want to talk about the topology, in which case you just take the underlying continuous topology of line bundles and so on. And the Chern classes are topological invariants. So that's where it all starts, the first Chern class of a line bundle. And it just encodes the natural notion of a degree. Now, higher rank bundles come in the obvious way. If you have a number of line bundles over a fixed space, then a section of each, you just write the simultaneous equations down, Sj equals 0, and then because they're common zero set Y, and each equation, at least generically, will reduce the dimension by 1, complex dimension, and so the homology will go down, the cohomology will go up, so the cohomology class of the zero set will lie in cohomology of dimension 2m, where m is the number of equations. So this is just, the theory of vector bundles is just the theory of linear equations with parameters, depending on the background space, either continuous, differentiable, analytic. Linear algebra with parameters is what the theory of vector bundles is about. And for instance, the global theory, how there is global information captured in the large. Now, if you have a collection of line bundles, then you can form the direct sum of these line bundles, which means you get a vector bundle of rank m. Obvious notion. And the collection of individual sections of the individual line bundles strung together gives you a section of the vector bundle. Same thing. Now, the Chern classes of a vector bundle, in the case when it comes from a sum of line bundles, is defined by the formula that I've written there. Let's say you put the Chern classes together into a formal polynomial. You write CR, t to the r, where t is an indeterminate. Call that the whole Chern class. You don't need to bother with the indeterminate t if you remember that there are different degrees. And now this is defined for a vector bundle as the product of the Chern polynomial for each factor in that direct sum decomposition. So the product of and if you write yj for the first Chern class of Lj, then you get the formula total Chern class of E is the product of 1 plus yj times t. So the Chern classes are the symmetric functions of the yj, which are two-dimensional classes. And so C0 by convention is 1, and the highest, largest value Cm is the class which is dual to the class of the zero section. So the notions of the relation between sections and their zeros of Chern classes goes up from line bundles to vector bundles in this way. The important formulas are such that the Chern polynomial behaves exponentially. It takes a sum into a product. And the point is, and here the key step comes that although a general vector bundle is not decomposable, it's not true that a general vector bundle, even topologically, can be written as a sum of line bundles. Nevertheless, it turned out to be very useful to copy the formulas you get from the decomposable case, and in fact to reduce the theory to that case, So the Chern classes are defined in such a way that the Chern class of the direct sum is the product of the total Chern classes, or Chern polynomials. And that's true even without assuming they decompose. So Chern classes are defined for all vector bundles. They have this nice multiplicative formula, and they are one of the basic tools of algebraic topology and of algebraic geometry, and they appear everywhere. And they encode information like we talked about before about the degree of a curve, the homology class of a cycle, generalizing the number of solutions of the equation, and those are all built into the generalization. Now, if we go from the complex numbers to the real numbers, we can mimic this in at least some formal way. You deal with real vector bundles, meaning families of real vector spaces instead of complex vector spaces. The real bundle, line bundle, section will then give you one equation over the real numbers, which in principle has one codimension less than the reals, one dimension less than the reals, so the dual class should lie in the first cohomology instead of the second cohomology. But now, because the real numbers don't have natural orientations, we can't control them with the integers, we have to work with integers modulo 2, so we get what are called the Stiefel-Whitney classes, which are the sort of real analogues, or the real poor relations, I would say, of the Chern classes. They're only defined modulo 2, and they have the same real dimension as the Chern classes have a complex dimension. They have half the dimension. So, but the same formula applies if a bundle is a sum of real line bundles, then total Stiefel-Whitney class can be defined in that formula as the product of the Whitney. First Stiefel-Whitney class is basically of the individual factors. So you can go through this very formal analogy and define the Stiefel-Whitney classes of a vector bundle. Now we come to the proper title of my talk, which is Real Geometry. And here with a capital R. Unfortunately, I use capitals all the time in transparency, so it's a very big capital to distinguish it from an ordinary size capital. Now, what I mean by this is the following. If you're an algebraic geometer, if you want to study an equation over the real numbers, you look for the complex roots first of all, that's the whole thing, and then you observe that if the equation has real coefficients, this algebraic variety you've got is said to be defined over the real numbers. And now it's true that if you have a root in the complex numbers, its complex conjugate is also a root, because the equations having real coefficients are interchanged by conjugating everything. So an algebraic variety defined over the real numbers doesn't mean that you're only looking at real points. There may be none, may be empty. It means you're looking at points in the algebraic closure, complex numbers, and you remember there is a complex conjugation. That only works if the coefficients of the polynomial are real. So you have real polynomials, but you allow complex roots. Then, of course, afterwards you can look at the real roots. And so now the fixed points of complex conjugation are the real points. So what you have is a complex manifold X, and the complex map it X to itself, which is anti-holomorphic. Conjugation is not anti-holomorphic. And the fixed point set are in the same real dimension as X has a complex dimension. So if X was a Riemann surface, XR would be a real curve. So these are the real points, and they are fixed points of the involution. This is already a particular bit of Galois theory. It's the case with the field, you're going from the real numbers to the complex numbers. The Galois group is order 2, and you study the action of the Galois group on the space set of all solutions. I call these, so what I'm trying to specify is that real geometry doesn't mean you only look at real things. What you define over the real numbers, but you allow yourself to look at complex roots which flip over under conjugation. Inside those there are the real points. So real geometry is this larger framework which has complex conjugation as a basic operation. Now, let me move now more specifically from algebraic geometry to topology. In 1966, I introduced sort of notions of this word real in a context which has nothing to do with algebraic geometry. We just start with arbitrary parameter space, compact space, or if you like a manifold, and you assume a continuous map, x to x, whose square is 1, which we call an involution. And then you look at a complex vector bundle over the space x, and you assume that there's a lift of the involution to the vector bundle, so over the point x, the fibre at x maps to the fibre at tau of x. But you assume that map is not complex linear, but antilinear. The fibres are complex, the map is antilinear, it anti-commutes with R. And that's what I call a real bundle. And I use that as capital R to distinguish it from ordinary real bundles, little r, which are just a naive thing when the vector spaces are real vector spaces, and you just mimic the complex story. So this is what distinguishes them. Down the bottom, you notice that if the involution is the identity, if it's trivial, nothing doing, then every point is fixed, and the xr equals x, and the two notions of reality coincide, because if you've got a point which is fixed by the involution, then over the fibre of that point, what you have is by definition an antilinear map, square 0, square 1, and that has plus or minus 1 eigenspaces over the reals, and the plus 1 eigenspace defines the ordinary real vector space, and what you've got is the complexification of that space. And a complex vector space with such a complex structure and a real part, its complexification, the two notions are equivalent. So whether you talk about the real space and its complexification, or the complex space and its involution. So when the involution is trivial, you recapture the ordinary theory of real vector spaces, real vector bundles. But if the involution is not trivial, then you've got something different. You've got a situation with a bit more structure to it. And now in the general case, what you have is a real bundle in this sense. On the one hand, you can forget about the involution. You just forget it, it's just a complex vector bundle. So it will have Chern classes in the ordinary sense, which will be ordinary elements of H2 R. But if you restrict the bundle to the set of real points, then this involution tau gives you a real vector bundle, or in fact the real points of the whole space E, and this will be a real vector bundle in the ordinary sense, and that will have Thiele-Whitney classes, which are covariant classes modulo 2 defined on the fixed point set. So we get, this will be the situation in algebraic geometry. You have this real vector bundle, I called it, which really means it's defined over real numbers, and now it has both complex Chern classes, which are defined in the whole space, and real Thiele-Whitney classes defined over the real points. And these are two different parallel sets of topological information. So that's, I mean, you have that information. And the question that naturally arises, so by the way, I defined these things a long time ago for various purposes, which I won't go into, and this theory develops quite nicely by itself, but the natural question is raised, is there a theory of characteristic classes? Chern classes, Thiele-Whitney classes, and some others are called characteristic classes. Is there a theory of characteristic classes which incorporates or gives rise both to the Chern classes and the Thiele-Whitney classes? These are classes are different. They live in different places. One is half the dimension of the other one is an integer, the other is modulo 2, and they're both there, and they're both defined from the same object. Is there some other theory which lives above, which specializes bound both these, and so you could say that a real vector bundle has real characteristic classes in some sense, which should generalize this? So that's the question you might ask. And I started to think about this a few years ago when I was worried about model 2 invariants of various kinds, like these Rockley invariants. And then I asked Andrew, it's a long time since I worked on this subject, perhaps something has been done in the intervening period. So, of course, being Andrew, he clicked a few buttons on the web and out poured a whole string of papers going from 1987 to 2012. Over this entire period, there are a lot of people who have studied this problem, and they come up with some answers. People thought it was worth the effort to do the work, and they solved the problem. Now, I didn't know about this. I wasn't looking at these things over 20 years, so I shouldn't be surprised that some people picked up the problem, made some progress with it. But I started thinking about it by myself, and one of the advantages of not knowing what's come before is that you might have an idea that other people haven't thought of. So I developed what I think is an alternative approach to this problem, which is well, interestingly related to what's been done, but it's not the same. And this is based on the ideas of Grothendieck, goes back more than half a century, and his development of K-theory. And I hope, I'll try to describe what this is. I hope this provides a new answer to this question, and it may lead to new results in real algebraic geometry. So it's a new approach which may be useful. As yet, I'll only claim that I can reproduce what other people have done in different ways. So let me now give you a quick positive summary of the bit of Grothendieck theory that we need to talk about. Now, in Grothendieck theory, you have an algebraic variety, and let's say you find out the complex numbers, and then you use sheaves theory. Now, sheaves are things like rings of holomorphic functions, locally defined, and they include sections of holomorphic bundles, those will be things, but also they include locally, over an open set, you're dealing with cumulative algebra, a ring of functions, a cumulative ring, and the sheaves locally are just modules. Modules over a ring, finitely generated modules. And there are two kinds of modules of interest. One are free modules. They correspond to vector bundles, locally free, given by basis of the vector space. And then also ideals, and the quotient by ideals, which give you the varieties. So, the standard example, going back to the same thing we've been doing before in different languages, is suppose you have your algebraic variety X, think of it as manifold, you have a line bundle, all algebraic, you take a section of it, you look and see where the section vanishes, you call that Y, that's our set of zeros, it's one dimension less, and then you write down, in the language of sheaves theory, an exact sequence, short exact sequence. What this sequence says is that you have a function on X, and then you can restrict it to Y. And locally, every function on Y can lift it back to a function on X. So the OY means the sheaf of functions on Y, algebraic functions, holomorphic functions. Similarly for X. And this map, X, Y locally, is surjective. So you put a 0 on the right-hand side of the exact sequence, but it has a kernel. And the kernel is generated by the ideal, those things that vanish on Y. Now in Y, given by one equation, is locally the principal ideal. That means that locally, the ideal space is itself locally free, therefore corresponds to a bundle, and what bundle it corresponds to is the sections of the dual of the line bundle L you started with. Because if you want to have a map from sections of L star to the trivial bundle, of X is then you need to multiply by a section of the dual to cancel the L part. So the section of L gives you a map from the ideal into the whole ring, just sort of a language to just describe elementary cumulative algebra. But now this is what Grothendieck did. He will now introduce his notion of K-groups of algebraic varieties. And the K-group is generated by sheaves of this type with the relationship that every time you have a short exact sequence, the one in the middle is deemed to be the sum of the other two. That forces a median group structure, which is called K of X. It's very sort of abstract, and it was a tour de force, but it turns out to be surprisingly useful and surprisingly simple. For any spaces, K of X is actually quite computable. But the important is within K of X, by definition, really, you have the equation I've written in red there, which says that the sheaf of functions on Y is the difference between the sheaf of functions on X and sheaf of sections of the line bundle L star. Now, we can go back to the rotation of bundles to the sheaves. The sheaf of functions on X we call 1, the trivial line bundle. The other one we call L star. So we then say, we write the sheaf of functions on Y, is equal to 1 minus L star in K theory. That's the sort of equation. And now, if you have a number of sections of line bundles, Lj, you can do the same thing for each one, and then the subvariety Y defined by the simultaneous equations, which now has lower dimension, its class will be just the product of the 1 minus Lj star, what I've written in green there. But the important thing is to remember that in this game, intersections of varieties correspond to products in K theory or in cohomology. This is the sort of fundamental duality relationship between intersections and products. So that formula is to be understood in that sense. Now, that's true if your bundle is decomposable as the sum of line bundles. But if you didn't, well, first of all, you observe that even in the decomposable case, you can expand that thing on the right-hand side, right in a way which doesn't use the decomposition. If you expand out the one product of 1 minus Lj stars, you can rewrite that as the alternating sum of the ith exterior powers of the bundle E star. The ith exterior power is a space given by skew symmetric products, rank I, it has dimension equal to the binomial coefficient, and this is really just more or less the standard expansion of the determinant in terms of its so this formula has the merit now, the right-hand side, of not referring to the individual factors. If you want to spell it out, you can write the individual factors back, but you can put them all together in that form, and then this is now true even if the bundle is not decomposable. So if you have a bundle E, and its section vanishes on S, then the class of Y, or chief, the Grothendieck class of Y, is just equal to the alternating sum of the exterior algebra of E star. It's a very nice simple formula. Now the point is that, well, I've written this down again, just to emphasize it, here it is. So for a general bundle, not necessarily decomposable, the class, or Grothendieck class of the sheaf of functions on the zero set is just equal to the alternating sum of the exterior powers of the dual of E. Now, here we make a bit of a sort of digression. I can't summarize all of Grothendieck's work in this sorting, but the whole point is that there is Feynman's theorem of Hilbert's, called the syzygy theorem. I think syzygy is the only word I know in the English language that has 3 Y's and no other vowels. I hope I've got the right order. The Hilbert syzygy theorem says that given any sheaf or subvariety or other kind, it always has a projective resolution by locally free sheaves. In other words, you can always write a finite exact sequence which starts on the right-hand side with the sheaf you started with, like Y, and writes down a sequence of vector bundles with homomorphisms which ends at some stage. So when Y is a complete intersection of divisors corresponding to line bundles, then you can write down that resolution explicitly in terms of the exterior algebra, like that. And Grothendieck showed that you can use different resolutions. The resolution is not unique. You see, what Hilbert's syzygy theorem says is that basically every ideal is finally generated, fundamental theorem of algebra. But then you look at the relations exist between the generators, and then that has a finite set of generators, and so on. And this builds up your resolution. And the theorem says if you start with a non-singular variety, it stops. It's finite. So everything can be resolved. And what Grothendieck showed with general homological algebra techniques is that he formed the alternating sum, the Euler characteristic formally, of the terms in that resolution. That, in K-theory, is independent of the resolution. So this formula you write down you could write any resolution of your sheaf Y, and you write down the alternating sum of the terms that appear in the resolution, and those all are the same for any of two resolutions, all the same within K-theory. So this has what it's doing now is giving you a lot of, you see, the cohomology class of Y, the zero set, is what we started off to think of as the thing that defines the Atiyah Chern class. But now we see that in K-theory, we've got much more information. A homology class in the Grothendieck sense of a subvariety, it carries the cycle, the topological cycle that you expect from that dimension, but it has much more information given from this resolution. I'll see that more in a moment. There's much more to the K-theory class than is given by the leading term in the homology. And this, for those of you who are old enough to be brought up in what's called obstructional theory, Chern classes and characteristic classes originally arose in terms of obstruction. You take a vector bundle, you look at where it vanishes, or look at where a frame vanishes, that's where it can't be trivialized, it's an obstruction. You analyze the geometry of those things, and that's how characteristic classes emerged. They were the things that obstructed a bundle from being trivial. You want to think of this the same way. The obstruction is the algebraic variety, but in Grothendieck's sense, the obstruction carries more information than just its homology class. But this obstruction class is formalized in the K-theory element. Now, Hinsel and I, after Grundig developed his K-theory, this is going back into the medieval mathematics, more or less, 1960s, we imitated all that in a purely topological context. We said, take a compact space, look at just topological vector bundles over it, and form a sort of what we call Grundig group, vector bundle out of vector, abelian group out of vector bundles, and we call that K of X, now purely topologically, nothing to do with algebraic geometry, but mimicking algebraic geometry. Now, in this context, the fundamental theorem is the theorem of homotopy theory, having to do with the nature of vector bundles and the unitary group, and the fundamental theorem is the Bott periodicity theorem. Glad to see that Bott was already mentioned by Robin Kirby in his lecture, and happy to bring him back to life again. The Bott periodicity theorem can be put in various ways, but in this formulation, the easiest way to say it is you take any space X and you multiply it by a two-sphere, then the K-theory of the product is isomorphic naturally to the K-theory of X tensor with the K-theory of the two-sphere. The K-theory of the two-sphere are simple, it's just free abelian group of two generators, one of which corresponds to the rank of a bundle, the other of which corresponds to the non-trivial bundle on the two-sphere with Chern class, the generator. So the periodicity theorem really is the part that concerns the interesting integers there. It says they reproduce when you shift dimensions by 2, and that's how you get periodic with period 2. By the way, these groups K of X, I should remind you, are commutative rings. They have an addition under addition of vector spaces of vector bundles. They have a multiplication under tensor product, and the ring structure is a very important part of the theory. It's very similar to cohomology ring structure. Now, the Chern class, in general, extends to an exponential map from the K-theory into the even cohomology. You just associate, you can define the Chern class not only a vector bundle, but also what you might call a virtual vector bundle. Down the bottom, I've written that out. A virtual vector bundle is formal difference of two bundles E and F. And you should define the Chern class, total Chern class of this, or polynomial, as the product CV times the inverse polynomial or power series of C of F. Then that formally extends it to K-theory. So the K-theory class goes into even cohomology with integer coefficients, and that is the Chern class defining K-theory. Now, the point, Bott periodicity theorem enables you to prove marvelous concrete results about these topological K groups, and you begin to get very friendly with them, and you realize they're really quite your friends, they're not weird objects, and in fact you easily see that they are abelian groups in the same rank as the cohomology, so they're roughly comparable with cohomology, and there are much more precise relations. So to a first approximation, K-theory is an alternative to cohomology for topological use. Now there's another relation between K-theory and cohomology. The first one is the one up there, which goes via Chern classes, goes from the K-theory to the cohomology. Another one, the other way around, going from cohomology to the K-theory. And this is a dotted arrow there, because that's not really a homomorphism of a map. It's more complicated. For those of you who know about it, it's called a spectral sequence. What it really means is there's a differential in the first space endomorphism with square 0. You can formally think of homology, and on that one there's another differential with square 0, and you keep going. And after a finite number of steps, you essentially end up with K. But these steps tend to be rather small, and not much happens in them. Very often nothing happens. So only a little bit of information is lost in going through this process. So K-theory, you should think of as very close to cohomology and has some advantages. Now the particularly nice case is if you have a space whose cohomology has no torsion, there are no elements of finite order, all the homology is free abelian. For example, this happens with nice spaces like complex spatial spaces and Grassmannians and so on. In that case, the results about the spectral sequence, you can forget about them, much simpler. What the theory says is that these K groups, space X, they're abelian groups, and unlike cohomology, they're not gridded by degrees, but what they have is a filtration, a decreasing sequence of subgroups, K0, K1, K2, and so on. And the associated gradient groups, what you get by taking each one and dividing it by the next one, taking the sum of those over all R, that is actually isomorphic to the even cohomology. So this is a group which is filtered, and it's only a graded group, the cohomology. It has more information, because the filtration, when you take this associated graded group, you're throwing a lot of information away. You don't worry about how they're tied together. This is familiar to group theories in all sorts of contexts. So in space without torsion, the K theory exactly reproduces cohomology. If you worry about the filtration is defined geometrically. Roughly speaking, it says that an element, a certain chain of the filtration, goes to zero if you restrict it to a skeleton of a certain size. So as you go up and up or down and down that chain, you get to things which live on higher and higher dimensional bits of the space. And in particular, if you go from R to R plus 1, you get the cohomology in that dimension. The next one will give you the cohomology in the next dimension. So this is because the structure of rings, and these are rings, and again, and the filtration presents the ring structure, there's a lot and lots of beautiful elementary algebraic results which come out of K theory which you can't get by cohomology. That's a much richer theory. Now, because the space is like complex space and its generalization, the Grassmannians, the thing that parameterizes linear subspaces of Cn, all of these are spaces with no cohomology, no torsion. You can apply this stuff to these, which are called universal spaces, because every vector bundle can actually be pulled back from a vector bundle on a Grassmannian. If you want to see whether something works, you just check it in the universal case, and then you pull it back. In the universal case, you can use all this beautiful machinery and forget about the torsion, and you can get very fast, very quickly. So that's a quick tour of what one does in K theory. Now, we're coming closer to the punchline. You have to allow time for the punchline. Now here, you see, Chern classes are things you can think of that you associate topological invariance to a vector bundle, to a K theory element. And the answer is in cohomology. But now K theory, as it turned out, can be viewed as an alternative way. You're replacing cohomology by K theory is somehow an improvement. So what you can do is to try and define what you might call internal Chern classes. Namely, if you've got a vector bundle, a rank M over a space, you try and define an internal Chern class. Now, what that means is it takes these values not in cohomology, but in the K theory. So I put a tilde on that. Now down the bottom, Bott had a nice terminology, rather macabre terminology. He called these cannibalistic classes, because they ate themselves. They took their values within the same thing from which you started. But the important part about them is that these classes, they lie in the, they lie in mth terms of filtration. So the higher Chern classes belong further and further down that chain. And you can define them just by our formula we had before. You define this Cm tilde of E, where E is an m-dimensional bundle, as this alternating sum of the exterior powers, and you prove properties about it, and you prove in particular that it only lives in sort of dimension m and higher, and if you take the filtration associated with this and factor it out, what you would get is basically the mth ordinary Chern class. E and F seem to be the same here, forget about that. So what we're doing is we're somehow ignoring that little bit about the spectral sequence and the torsion. E is telling you that it's not quite true as it stands. Basically what these internal Chern classes do is they lift the Chern class from cohomology into K theory. And if I told you that K theory has more information, these Chern classes give you a much stronger hold. They're topological still. And they start off with the mth Chern class. By the way, this gives you just the mth Chern class. If you want to get all the Chern classes, you just shift the degree of the rank of E by subtracting trivial bundle, and you apply the formulas, and it'll all go through. So here's the idea that you can define, and this is really ideas of in algebraic geometry from Grothendieck, which we copy in topology. Now, if you work, because these groups have the same rank, you can work over the rational numbers, and you lose a bit of information if there's torsion, and you don't lose information if there isn't torsion. But very often the formulas of the rational numbers are much more elegant. So over the rational numbers, the total Chern class, defined up there for you, but you can define what's called the Chern character. The Chern character is defined as the sum of the exponentials of the classes. Now, an exponential of a two-dimensional class is just a formal. It just means you expand the power series, and eventually it stops because you get above the dimension of the space. But you write the exponential. These are called the Chern character. Of course, because of the factorials in an exponential power series, it's only defined if you're allowed to divide. So it's only defined over the rationals. But now the point is that this map gives you a map from the K-theory to the cohomology over the rationals, even cohomology, which is actually a ring isomorphism. And so it preserves multiplication, addition, and over the rationals, it's an isomorphism. So the Chern character identifies the two things completely. But of course, it has thrown away a certain amount of information to do with integers, so you don't always want to do that, but you see what's going on more easily. So for example, this tilde Chern class that I talked about, which is a K-theory class, if you take its Chern character, then that converts it into ordinary cohomology. What you get is the product. For one, you see what each factor we had before, we took 1 minus Lj star, and so you get 1 minus e to the minus y, the minus corresponds to the star, and so you get this power series. Now, that power series begins, if you remember, the product of all the yj's is the ordinary nth Chern class. You take out that outside, what you're left with is a power series beginning with 1. It's an invertible power series. And the inverse of that power series is called T. And that is the same as Todd power series. The expression there, the product of those factors you expand it and write it in terms purely formally, the symmetric functions of the y's, those are called the Todd polynomials, which play a very key role in the Riemann-Roch theorem. This is Grothendieck's approach to it. So what we're doing here in defining these refined Chern classes, or the lifted ones, or the K-theory ones, is they differ from the ordinary Chern classes by these Todd polynomials. They start off the same, but they have a big tail, which contains a lot of interesting information. And that is that you see over the rational numbers, but the formulas I gave you before didn't require you to go to the rational numbers. Now, punchline just coming in now. And that is, what does it all have to do with real vector models? Well, the idea is that, you see, if you do things in a natural way, you don't need to think. Start now with a space X with an involution. You define the K-theory of these real bundles, real with a capital R. We call that KR of X. It's a ring on the tensor product. It has exterior power operations. It is filtered by dimensions, all as before. And you can define internal Chern classes in this theory exactly in the same way as before, by the same formulas. So here is a candidate home. These real vector bundles have natural classes living in their natural group, which is the natural group associated to K-theory. It's almost the same as cohomology, but it's not quite. And if we... Are we advertising Panasonic? Sorry, this is our sponsor, is it? If we just go to two things. If you forget about the involution, then you obviously recover the previous definition we gave in K-theory, in the ordinary K-theory. If we restrict to the real sets, then over the real sets, this real K-theory becomes ordinary real K-theory, and everything you do over ordinary real numbers is the same. Exterior power is the same formulas, and you'll get exactly the same formulas, and now involving Stephen-Wheatley classes. So, it's a procedure which works without thinking. You just follow what you've done before, and you automatically get the answer. Now, what you have to do, if you want to compare it with what's been done, you have to do a bit of work, which I'm not going to do. I'm too lazy. But roughly speaking, in the literature, you'll find that the characteristic classes that they define live in the equivariant cohomology of the space with respect to the evolution, but where the integers are twisted or are allowed to act by the evolution as well. In that theory, then that's where they have their Chern classes. This should be compared with what I've been proposing here. And they have one nice formula which I can derive too if I had time. And that is that these classes of theirs, if you restrict them to the real points, then besides the Stephen-Wheatley classes, the W's, they actually get, the Stephen-Wheatley classes are real and have half the dimensions of the Chern classes. So the restriction isn't really a genuine map of cohomology classes, but if you combine it with the cohomology coming from the group of order 2, then you call the generator that U, then there's a nice formula that tells you these Chern classes restrict to something kind of the Stephen-Whitney class, W, together with the Stephen-Odd square operation. Now, I'm not going to go into that. Those of you who know about Stephen-Odd squares will see this is a nice formula, and you can use reference one of my papers to see how to get to it. So I've just got time to finish by giving you, now I could give you a long string of references because lots of papers have been published in the past, present. I just selected 3. The first is the paper I wrote in 1966 about introducing this real K-theory in reality. Second is this paper, which is not yet been published. You see how up to date it is, by Pitch and Shearer, 2012, and it's about this formula I just mentioned down there. And the third one is another old paper of mine, where I show how to relate power operations and K-theory, and that's the one you have to use if you want to understand the analog of Stephen-Odd squares in this game. Well, as you see, I've done basically nothing. I've given you a quick tour d'horizon of vector bundles, algebraic geometry, and K-theory, summarizing the mathematics of the last 50, 60 years. But I tried to focus on just the simple ideas about Chern classes of line bundles using the vector bundles and the formulas involving alternating sum, powers, exterior powers, which is a very important formula, and that you could develop a theory of characteristic classes entirely internally within K-theory itself. It sounds circular, it sounds like you're doing anything, but what you're doing is starting with a vector bundle or an element of K-theory which is spread over the whole space. Then you map it into these elements here, which live in higher and higher dimensional bits of the space. If you look at the leading bit, you get the original Chern class, but you get also a tail of further information. And then you can do that over the real numbers, with the real operations. And so this is, hope that because this is geared naturally to the technology of algebraic geometry and real numbers, this will be one of the tools one could use in trying to understand more about real algebraic geometry. Now that's a test to be carried out. I've got a few ideas, a few things I'd like to prove. I mean, I'll give you sort of one thing I started with, and vaguely when I talked about Rockley's theorem and 4 manifolds, this is what I had in mind, is that the nice theorem in algebraic geometry, which a lot of these things come back to, is the Riemann-Roch theorem, telling you how to compute the alternating sum of the dimensions of cohomology groups, chief cohomology groups of compact algebraic variety, just sort of formula, generalization by Grothendieck, and then topological analog by myself. This is a nice story which works very well for complex manifolds. The question is any part of that story still relevant to the real parts of algebraic varieties? Are there theorems that relate dimensions modulo 2 of spaces of solution on real points? I mean, is there some way in which we can get a really powerful theorem for real algebraic geometry which mimics what we know in complex algebraic geometry? If so, this apparatus I've been sketching the outline of here would be a natural starting point, natural tool to put in your kit bag. We'd be able to go along following what's been done in the complex case and know that more or less by just imitation we could get something in the real case. But it remains to be seen whether it, ends of a long, hard work, you may find all you've done is to reprove something we've done before, or you may get, I've even written down beautiful formulas which say A equals B. It looks very exciting until you realize that both A and B are 0. It's a correct theorem, but not very interesting. So then you can check it up sometimes. You can, even when the theorem says 0 equals 0, you may think it's very dull, but if you allow things that depend on parameters, you may find behind the scenes there's something interesting. And algebraic geometry with parameters is what's called the study of moduli spaces. Algebraic varieties, which are the same topological class, they can vary their isomorphism class depending on some parameters forming a moduli space, then you can try to study vector bundles on the moduli spaces, and that's a big industry. So, and maybe that things are zero on one fibre, but not zero when you vary them in the sense. So there are possibilities, but I don't want to make too much propaganda for something that doesn't yet worked out, but it's something a young chap somewhere might pick up. And anybody has any bright ideas, please send your answer on one sheet of paper, and I will consider a prize for the best solution and pin it up on the notice board. Thank you.
Any questions?
Do these characteristic classes that you've been talking about say anything about those configurations for Hilbert's 16th problem?
Good question. Well, you see, in preparing this talk, I only got around to looking at the Hilbert 16th problems a couple of days ago, haven't I? That's the kind of thing I'd like to see. And the point is that the work of this Russian school, Gudkov and Arnold, has made progress with these Hilbert 16th problem, and they've used methods from algebraic geometry, and in the lowest dimensional cases, because probably a lot of this machine I'm talking about may not be, you can do it perhaps more elementarily, and so that may be what they've been doing. So, yeah, in principle I hope so, but I haven't checked it out. It's something you can do. And I've given you all the hints.